All right, let's talk a little bit about partial pressures and the equilibrium constant. Up to this point, we've been using molarity to get equilibrium constant, but you can use pressure if your equilibrium's in the gas phase. It's derived in very similar ways using partial pressures instead of concentrations. And we can kind of derive it from PV equals nRT. If you solve for P is equal to nRT divided by V. Now, N divided by V, if V is in liters, is molarity. So you can say that pressure is equal to molarity times RT, or molarity is equal to pressure divided by RT, which will allow us to convert from a KC to a KP. But there'd be a function of 1 over RT and all of the exponents that you have to work with. So if I've got 2 chlorine gas plus 2 water gas going to form 4 HCl gas plus O2 gas, we can see the Kc and the Kp have very similar forms. HCl to the 4th times O2 divided by Cl2 squared and H2O squared, except the Kp, it's pressures, and they need to be in ATM, or molar concentrations in the case of Kc like we've been working with. The functional form is very similar. And so to interconvert, it would be a number of RTs. And so we'd have to plug in P divided by RT into each of those places. And then you could pull out the factors of the RTs. And I'm not going to ask you to drive this on the test, so don't sweat that. But what you can see is that for this particular reaction, there seems to be a factor of 1 over RT to the 5th in the numerator, 1 over RT to the 4th in the denominator. So all but one of those cancel. So Kc equals Kp times 1 over RT. So Kc equals Kp times RT raised to the -1 power, or Kp equals Kc to RT to the +1 power, which you could omit in our case, but I'll do it for sake of completeness so that you understand what's going on. R equals, in all these cases, 0.0821. But the issue is that those 1 over RTs is based on the stoichiometry of the reactant versus the product side, and how many of those RTs will cancel. It'll be different for each reaction if the stoichiometry and the number of reactants and products and whatnot are different. So in general, we can say that Kp equals Kc times RT raised to the delta N power, where delta N is the difference in the number of moles between the products and the reactants. So it's going to be gaseous moles of products minus gaseous moles of reactants, or Kc equals Kp times RT raised to the negative delta N power. Either way. So we'll start off working a problem that's just a basic Kp problem, then we'll work one where we do the interconversion. So let's say we got nitrosyl bromide and OBr, and it's 34% dissociated by the following reaction at 25 degrees Celsius at equilibrium in a vessel where the pressure is 0.25 atmospheres, which that's what has to go into Kp, so we're okay. And so we want to know the value of the Kp. So this is a little bit different equilibrium problem than we've worked. You could work a problem like this with concentration as well, but we'll just do something a little different so we're not doing the same problem over and over. But in this case, I know the total pressure of all the gases in the container, but not the pressure of any one in particular. But I know how much it's been associated, so we can work with that. Okay, so let's look at the problem. We've got a reaction 2NOBr in equilibrium with 2 NOs and Br2. But all we know is that it's 34% dissociated and that my total pressure is 0.25 ATMs. I don't even know how much of this I'm starting with. So it's a little bit different of an equilibrium problem, but it's just a basic equilibrium problem. We're just going to use pressures instead of concentration at this point. So we're going to have our initial, our change, our equilibrium, just like before, except everything in the table is going to be pressures. So this will be pressures of each of these. So pressure NO BR. This will be pressure of NO. This will be pressure of BR2, all in ATMs. So since we don't know, we'll give it a variable. And since it hasn't dissociated yet, we assume we got no products. But we know it's 34% dissociated, so we can say X minus, or we can say minus 0.34X. And so our equilibrium would be 0.34 X minus 0.34 X, and this would be plus, no. Now we got to consider the stoichiometry. And so this will be the same since the coefficients are the same. So this will be plus 0.34 X, but this will only be plus 0.17 X because there's no two coefficients. So it's going to change by half as much. So this will be 0.34 X, 0.17 X, and then we got the combined like terms here. This will be 0.66 X. Now we use our total pressure. And so we're going to say 0.66 X plus 0.34 X plus 0.17 X is going to equal 0.25 ATMs. But we just need to combine like terms. So that's going to be 1.17 X equals 0.25 ATMs. And then so X is equal to 0.21 ATMs. Now I can get the pressures of. Okay, so let's take a look at that. And once we know what X is, so we've got for our pressure of our NOBR, we've got 0.66 X. For our pressure of NO, we got 0.34 X. And our pressure of BR2, we've got 0.17 X. Then we just have to plug in, since we know what X is, 0.66 times 0.21 ATMs is equal to 0.14 ATMs. 0.34 times 0.21 ATMs is equal to 0.071 ATMs, and 0.17 times 0.21 ATMs is equal to 0.036 ATMs. So lastly, we've got to write an equilibrium constant expression, Kp. So it's going to be products, NO squared, partial pressure of BR2 divided by partial pressure of NOBR quantity squared. And then it's really just a matter of plugging and chugging the numbers from what we've already calculated. So NO was 0.071 ATM squared, BR2 0.036 divided by 0.14 squared. And so it's going to be 9.3 times 10 to the negative third power. And that would be our answer. Okay, so part B of this particular question would be finding the value of the Kc now that we know the Kp. And so that's easily enough done. Here's some of the work we did on the previous part. But let's remember to do the Kc part. Here's the reaction again. So we need that delta N. So if you look, you got 1, 2, 3 moles on the product side, but only 2. So our delta N, since it's products minus reactants, will be equal to 3 minus 2, which is equal to 1. That would be 1 mole. Now it's just really plugging into this. So Kc is going to equal our Kp that we calculated in the previous part, 9.3 times 10 to the negative third times R, 0.0821. That's liters ATM per Kelvin mole, but we're not going to track the units quite as much because equilibrium constants are unitless. T, we said, was at 25 degrees Celsius in the previous problem. And so we'll call that 298 Kelvin. And all that's raised, since it's a negative sign there, we're going to raise that to the -1 power, but just what's in parentheses here, not this. And so then you have to run that through your calculator. And then you'll get 3.8 times 10 to the -4th power, and that would be your Kc. All right, let's talk a little bit about heterogeneous equilibria and how they affect Kc and Kp. Heterogeneous equilibria have more than one phase present in equilibrium, which we haven't really talked about at this point. For example, if we got solid calcium carbonate forming calcium oxide, both solids, but carbon dioxide's a gas at 500 degrees Celsius. So how does the equilibrium constant differ? Pure solids and pure liquids do not appear in equilibrium constant expressions because they have activities equal to the unity, and that is their concentration doesn't really change very much. Solvents and dilute solutions are essentially the same thing. So solids and pure liquids like water, we're not going to account for. So for that reaction of the calcium carbonate, we're going to look at it. The Kc would be equal to the concentration of that CO2 gas, or the Kp is equal to the pressure of the CO2 in the container. Since it's the only one, it's the pressure, not the partial pressure. But it's a little bit more complicated if we look at example 1512. We got SO2 aqueous, water liquid, and H2CO3 aqueous. Again, expressions for Kc and Kp. Water is a pure liquid and will not appear in the expression. So let's write it for Kc and Kp. So let's start with Kc. Product, concentration of H2SO3 divided by concentration of SO2. We leave the water out. This will be important as we go forward into the next chapter talking about acid-base equilibrium. Kp, you're going to have trouble writing an expression for Kp, so there's no expression you can write. And the reason you can't write an expression is there are no gases, and Kp is only based on gas phase substances. And so only gas phase substances will show in a Kp.